Have you ever wondered why a seemingly simple step like sample preparation can make or break your analytical chemistry results? When it comes to analytical chemistry, it's not just the fancy instruments or the complex formulas that matter. In fact, the first and perhaps the most crucial step in the process is sample preparation. Imagine you're an artist and your canvas isn't clean. No matter how vibrant your colors are or how unique your style is, the final masterpiece will be influenced by the remnants on the canvas. Similarly, in analytical chemistry, the canvas is your sample. If it's not prepared correctly, the results will be skewed, no matter how advanced your analytical techniques are. Sample preparation involves transforming your raw sample into a format suitable for analysis. It's like prepping your ingredients before cooking. You wouldn't throw an entire potato into a stew, would you? You'd peel it, cut it, and maybe even boil it first. That's what sample preparation is all about. But it's not just about making the sample fit for analysis. During this process, we also separate the analytes, the substances we're interested in, from interferents, the substances that could interfere with our analysis. This is like separating the wheat from the chaff, ensuring that our results are accurate and reliable. Now, there are numerous ways to do this, each suited to different types of samples and analytes. Some techniques are based on size, where larger particles are separated from smaller ones. Others are based on density, where heavier particles sink and lighter ones float. We also have complexation techniques that involve forming complexes with specific ions, and liquid-liquid extraction, where substances are separated based on their solubilities in different solvents. These methods are not mutually exclusive, and often a combination of techniques is used to ensure a clean, representative sample. It's like a well-orchestrated dance, where each step is integral to the final performance. So it's clear that sample preparation is crucial, but how do we actually go about it? Let's find out. Before we even delve into the analysis itself, we must first prepare our samples properly. Now let's imagine you're a detective. Your mission? To unravel the secrets held within an unknown substance. Your first step? Choosing the right sample, of course. It's a bit like picking the perfect apple from a tree. You wouldn't choose one that's rotten or bruised, right? Same goes for your sample. You need a representative chunk that will give you the most accurate results. Once you've got that perfect sample, you need to handle it with care. Think of it as a precious artifact. Any contamination can skew the results and lead you astray, so gloves on, folks, and don't forget to clean your equipment thoroughly. Now comes the preservation. Not all samples can be analyzed immediately. Some need to be stored for a while, and this is where preservation comes in. Preserving your sample prevents any changes that could occur over time. It's like putting a pause button on your sample's properties. This could involve refrigeration or adding certain chemicals to prevent decomposition. And speaking of storage, it's not just about chucking your sample in the fridge and hoping for the best. No, it needs to be stored in a specific way to maintain its integrity. That could mean storing it in a dark place to prevent light-induced changes, or in a sealed container to avoid contamination. So why is all this fuss about sample preparation important? Well, it's because these steps greatly impact the overall results of your analysis. A poorly prepared sample can lead to inaccurate results, and in the world of analytical chemistry, accuracy is king. Now that our sample is ready, what's next? We need a plan. A good scientist always has a plan, especially when it comes to sampling. Let's dive into the intriguing world of sampling plans. In the realm of analytical chemistry, a sampling plan is a well-thought-out strategy that guides us on what, where, when, and how to sample. It's the roadmap that leads us to the treasure trove of data we're after. Consider a sampling plan as a chef's recipe. Just as a chef carefully chooses the right ingredients, we select the most representative portion of the material for analysis. The plan helps us avoid bias, ensuring our analysis is a true reflection of the entire sample, not just a skewed snapshot. It's like planning a journey. We have to know our destination, the stops along the way, and the best route to take. And in analytical chemistry, that destination is accurate data. Once we have our plan, it's time to separate the wheat from the chaff, or in our case, the analytes from the interferents. Separation is often necessary in chemistry, and we're not talking about breaking up. Now let's dive into one of the most crucial aspects of sample preparation, separating analytes from interferents. But first, what exactly are analytes and interferents? Well, analytes are the substances we're interested in studying, while interferents are other substances in the sample that could interfere with our analysis. Think of it like trying to listen to a specific instrument in an orchestra. It becomes much easier if we can somehow mute the other instruments. So how do we do this separation? Various techniques come into play depending on the nature of the substances involved. One of the most common methods is filtration, where we use a barrier to separate solid interferents from liquid or gaseous analytes. It's like using a sieve to separate pebbles from sand. Another technique is distillation, where we separate substances based on their boiling points. Picture boiling a pot of salty water. The water evaporates, leaving the salt behind. The evaporated water, now free of salt, can be collected and cooled back into a liquid. Chromatography, on the other hand, separates analytes based on how they interact with a stationary phase and a mobile phase. Imagine a race where each runner has different strengths and weaknesses. Some might excel on flat surfaces, while others are better at uphill climbs. The same principle applies to chromatography, with the stationary phase acting as the racetrack and the analytes as the runners. These separation techniques allow us to isolate the analytes from interferents, improving the accuracy of our analysis. It's like trying to understand a language. It's much easier when you can focus on one word at a time rather than a whole sentence. Separation doesn't stop there. We can further refine our sample based on size, density, complexation, and even through liquid-liquid extraction. So stay tuned as we delve into these advanced separation techniques in the next part of our journey through the fascinating world of analytical chemistry. Just like in life, in chemistry, sometimes we need to get a bit more specific with our separations. Now let's delve into the more advanced separation techniques. First up, we have separation based on size. This is a bit like sorting your laundry by the size of clothing. In the same way, molecules can be separated based on their size, using techniques like gel permeation chromatography. The larger molecules are unable to enter the pores of the gel and are eluted first, while smaller molecules enter the gel and take longer to elute. Next, we have separation based on density. It's similar to how oil floats on water due to their density difference. Techniques such as centrifugation exploit this principle. The denser components in a mixture settle at the bottom, while the less dense ones float, allowing us to separate them. Now, let's move on to complexation. This technique is a bit like a dance, where two molecules form a complex and separate from the rest. A classic example is the use of ethylenidiamine-tetraacetic acid, or EDTA, which forms a complex with metal ions and aids in their separation. Finally, we come to liquid-liquid extraction. Imagine trying to separate a drop of oil from a cup of water. You could add another liquid, say hexane, which is more friendly with oil. The oil would prefer to mingle with hexane, separating from the water. In chemistry, this principle is used to separate substances based on their solubility in different solvents. Each of these techniques serves a unique purpose and is chosen based on the nature of the sample and the components we aim to separate. From separating large proteins in a biological sample to isolating metal ions in a water sample, these techniques equip us with the tools to delve into the intricate details of our samples. So there you have it. From preparing your sample to separating it into its key components, these steps are vital in the world of analytical chemistry. It may seem a bit complicated, but every step in the sample preparation process plays a vital role in getting accurate results. Remember, the journey begins with preparing your samples for analysis, a meticulous process that ensures you're starting with the most representative piece of the material under study. Then comes the significance of a well-structured sampling plan, which provides a roadmap for conducting your analysis in the most effective way possible. Don't underestimate the power of a good plan. Next, we learned about the art of separating analytes from interferents, a crucial step that helps us to focus on the substance we're actually interested in. And finally, the advanced separation techniques based on size, density, complexation, and liquid-liquid extraction give us the tools to effectively isolate our desired analytes. All of these steps combined ensure the accuracy and reliability of your analytical results. Subscribe for more because you won't find me later. Until next time, keep experimenting.